Hi, I'm Mark Weitzman. Welcome back to our final part on our deep dive transformation of a W boson particle state. So just to review the problem again, we have a W boson that's moving in the Y direction with momentum Py in O's reference frame. And there's another observer O prime which is moving with velocity V in the Z direction in O's reference frame. And the question is, how does O prime describe the particle state of the W boson? Now, from special relativity, it's easy to figure out what the momentum is in O prime's frame. So the only thing that's a little bit special in this is, what is the polarization? What's the spin? And what we've established in the previous parts is that because we have two boosts in a row, a boost from the particle's rest frame to where it's moving with velocity Py, momentum Py in the Y direction, that's one boost. And then we have another boost in the Z direction with a parameter, velocity parameter of minus V in the opposite direction. So what's involved is two boosts in a row. From special relativity, we know that two boosts in a row ends up being one boost plus a rotation, or a rotation plus a boost. And what we've established is that the under the boost from rest, the spin components don't change, but under a rotation, of course, they do. So we've calculated, we wrote the rotation as a product of three boosts previously, and I'm just going to write it down symbolically. We had some kind of boost with a certain parameter, inverse boost with a certain parameter, boost with a certain parameter, and another boost with a certain parameter. And we wrote down all three of these matrices, and I said what you need to do is you have to multiply these three matrices. And I used both hand and software, and actually I found it easier to do by hand than by software, because the software for some reason wasn't doing the simplifications as well as I thought they should. But in any event, I finally arrived at the following following matrix. And I'm using the Weinberg Chapter 2 convention, where the fourth row corresponds to the time. And even though it took a while for all this to simplify, it actually does simplify, as you can see with all these ones and zeros. And just to remind you that the gamma P is associated with the gamma that would be associated with a particle moving with momentum Py. Gamma V is the gamma that would be associated with the velocity V. Okay, so when you do a long calculation and you get a result like this, which often happens in quantum field theory, Compton effect will be an example we'll see later on. It's nice when everything simplifies. Just looking at this matrix, you can say this looks like a rotation matrix. For one thing, the time completely separates out, so there's no effect on time components. The other thing is it looks like a standard rotation matrix where we're rotating around the x-axis. And that's good because when you have a boost like this and then another boost like this, you end up getting a little rotation in this plane, and it's about the axis perpendicular to this. So here we had a boost about y, we had a boost in the Y direction, a boost in the Z direction. We expect to get a rotation in the X-axis, and it looks like that what we got. Plus, we have the anti-symmetry here. So it looks exactly like our standard rotation about an axis in the form like this. So what you'll get is you'll get cosine theta and if you think about it, you can verify these signs and that the angles are right from the boosts. Now, obviously this needs to be an orthogonal matrix to be a rotation matrix, and you should verify that cosine squared theta plus sine squared theta equal 1. I'm not going to do that here, but if you actually go through it, you'll see it works out. So we have our rotation matrix, and remember our Lorentz transformation is essentially lambda equal to a rotation matrix, which we just calculated, times a boost with some parameter. As I said, the boost doesn't change the spin components, so if I want to get the new spin components, I just have to do the usual rotation matrix. Now at this point, there's two ways to proceed. One is you can use the spin representation. In this case, it would be spin 1 representation of the rotation group. This involves sort of going to one of your group theory books to get the right conventions and everything. Tung is a very good example. I think it was published in 1984. He does this, and you use you go to the tables and you use your D matrices. Now, some of you might not remember this stuff. I'm sure all of you remember your like Gordon coefficients and this table from the particle physics book and online, and use these things a lot. But if you notice that they have these little D things all over the place, well, these are the representation matrices. Here's the spin 1/2. The top part gives the spin, and then these give the components. You might recognize the half angle and the cosine and the sine for the spin 1/2. Well, here's the ones you would use for the spin 1. And if we were ever so brave to do a spin 3/2, you'd use these, and a spin 2, you'd use these. I did it this way at first, just to make sure that I was doing it right, but you have to remember all the conventions and you have to be consistent, and it usually requires going back and looking at some kind of book like I did. So you can do it that way. In this particular case, since we're dealing with a spin 1 particle, the alternative way is just to remember that a spin 1 particle, a massive spin 1 particle, is a vector particle. You may have heard that phrase. That's why we have vector gauge bosons. That's what a W boson is. It's a vector boson. That means it transforms just like a vector. So now, there's only one thing you have to be careful about, is if you're going to use this matrix, this is in a Cartesian form, x, y, z. So now we don't have to worry about the time part. For those of you who know about special relativity, there's always like, if you use like a spin vector to represent spin, the zero component in the rest frame is 0, and you write this covariantly, something like P mu S mu equals 0 is a covariant way of writing that constraint. So we have this 3 by 3 matrix, and so we just have to remember to use Cartesian components. And here again, if you go back to a quantum mechanics book or some kind of reference book, they'll have these basic transformations. Here again, you have to use the convention. I'm using the convention that Weinberg uses in his book. At least later on he uses. So here, if I want if I have plus, minus, and 0 represent the spherical representation, the spin, the one where the z is diagonalized, and then x, y, and z represent the Cartesian components of spin. So you use this transformation. Not too hard. And then the reverse transformation is simply v plus 1 equals, like I said, different books will use different signs for these things. You just have to be consistent. So for example, if we had our original spin was like 1, 0, 0, let's call this like a plus 1 state, plus 1 spin state, and this is the spin part, we would first transform this into the Cartesian state, which would be, still write it as a column vector, square root of 2. Just using these transformations. Here we have v plus 1 is 1 and minus 1 and 0 are 0. So you plug in here and you get the Cartesian components. Now you multiply by this matrix and you'll get some other components. I'm not even going to write them down. I'm going to attach a PDF or a file of my calculations, but you'll get Cartesian components here. And then you're going to transform them back to spherical components. And so I'm just going to write Cartesian. C. This is spherical. This is C. Transform them back to spherical. And the final result is going to be something like, if you started with a plus 1, it's going to go into a 1/2 plus 1/2 gamma p gamma v, 1 plus gamma p gamma v, I over the square root of 2 py v, should be py over m, v gamma v, then divided by, again, 1 plus gamma p gamma v. I know this is hard to read, but then the final one would be minus 1/2 plus 1/2 gamma p gamma v, or 1 plus gamma p gamma v. So this brings us to the end of this deep dive, and what I wanted to impart on you is that in the rest frame of a particle we can apply normal quantum mechanics, normal non-relativistic quantum mechanics, use everything we know about how spins transform, and then we can do a relativistic boost. We can separate out the relativity part and the quantum mechanics part for a particle transformation. And this method is we can use for massless particles as well in a different way. It's more complicated with photons because we're missing a spin state, and we end up getting a gauge transformation under a Lorentz transformation as well. But the main thing is that this whole theory was developed by Wigner, and you'll hear it referred to as the little group. And if you want to pursue it further, I recommend you read chapter 2 of Stephen Weinberger's book on the quantum field theory of fields, Volume 1. And he goes into it in great detail. And most books talk about or do a little bit with the little group. It's sort of the invariant group. That's what we calculated here. This R theta is just a little group. And in my notes, I might call it W or something as the little group element. But so that's all I wanted to say, and I'll see you further on the next part, our lesson 3 on canonical quantization. Thank you very much.